for reminding me. So the recording is started now. Okay. Um, so covariance represents somewhat what is called a linear dependence between two random variables x and y. Linear dependence means if x and y is linked by a linear equation. Linear equations are equation of straight lines like ax plus by is equal to c, those kind of things, or y is equal to 3x minus 5, this kind of thing. So if x and y are dependent in some sort of a linear function, that will be captured by high covariance, and if they are not linked by some approximate linear function, you will see some kind of low covariance. This is the basic idea behind covariance. We will explore about that. And the next formula, which is written in the blue box, is alternative formula of covariance. The first formula, which is written in the first blue box, is the original formula of covariance, and the second one is the alternative formula of covariance. Now, if you ask how did I get this alternative formula, I would tell you that this is actually a good exercise. If you have understood how I got the alternative formula for the variance, this is exactly the same steps of computation. Okay, if you follow the exactly same step of computation, when I was computing the alternative formula of variance from the original formula of variance, you can get this alternative formula of covariance from the original formula of covariance. Only thing that you need to keep in mind that this expectation x and expectation y are constants, and you manipulate with that, you will get the alternative formula of covariance. Okay. So next I gave an example of covariance, but before going to that example, this example is actually a little bit extensive. Let me tell you a few other things about covariance, and then we will come to this example. Okay. Because since my laptop is not responding very fast, so I will come to this example at the end of today's lecture. Let me tell you a few other important things about covariance. Okay, so scroll down. Okay. All right. So next, what I want to say about covariance is that covariance is usually calculated between two random variables x and y. Okay. But just for fun, if you want to calculate covariance between x and x, okay, which usually people do not do, but if you calculate covariance between x and x, from the formula it will be expectation of xy. It was the covariance formula was expectation of xy, but since it is x and x, it will be expectation of x times x, which is expectation of x square, minus it was expectation of x times expectation of y, but since again it is y is same as x, it will be expectation of x whole square. So essentially this is variance of x. So covariance between x with itself is same as the variance. You can think of it in this way: if you are finding covariance between x and x, then essentially y is equal to x, right? Usually we find covariance between x and y. But if I am doing covariance between x and x, the second component was supposed to be y, but if I replace that by x, essentially y is equal to x, which is a very high linear correlation, and you get variance. Actually, that is very high. And second formula, which is written in B, and this is actually probably the most important takeaway of this part 2 of today's lecture. The formula B, or part B, is the moral of this part 2 of today's lecture. So part B is variance of x plus y. So if you have two random variables x and y, so you have x on one hand, y is on other hand. If you want to calculate variance of x plus y, the actual formula of variance of x plus y is variance of x plus variance of y plus covariance of x and y. So there will be this extra covariance term, covariance of x and y. It is not very important. It is not variance of x plus variance of y. If you compare with the expectation formula from the previous lecture, expectation of x plus y is always expectation x plus expectation y. No matter whether x and y are dependent, independent, whatever. In fact, you had a quiz problem. So expectation of x plus y is always expectation x plus expectation y, even if x and y are dependent. However, for variance, the same is not true. For variance of x plus y is variance of x plus variance of y, plus you will have a extra covariance term. So is someone trying to ask a question? And below I tried to outline the proof of this fact, why variance of x plus y is equal to variance x plus variance y plus 2 times the covariance. Once again, the trick I have used in the proof is exactly same or almost same as the trick of the alternative formula of variance. So at the beginning of today's lecture, I gave the original formula of variance and then I deduced an alternative formula of variance. The same trick is going to be used again and again. So the same trick is used here to calculate the variance of x plus y. So variance of x plus y by definition is going to be expectation of x plus y minus expectation of x plus y whole square. That is the original definition of variance. Now you can split this expectation of x plus y by expectation x plus expectation y, which is written on the right side note. So if you do that, here it becomes expectation of x minus expectation x plus y minus expectation y whole square. Okay, very simple algebra here. X plus y minus expectation x plus expectation y. So you can put x and x together, x minus expectation x plus y minus expectation y. Take the whole square and then you expand binomial expansion. Again, very high school basic elementary mathematics here. So the first terms becomes x minus expectation x whole square plus y minus expectation y whole square plus 2ab, right? So this 2 times x minus expectation x plus y minus expectation y, and there is expectation on outside of each of the each of those expressions, and which gives you variance x plus variance y plus, very importantly, 2 times covariance of x plus y. So if when you do variance of x plus y, you have this extra 2 times covariance of x plus y. Okay. Since my program is not responding very fast, let me pause here for a few seconds and see if anyone is having any questions, because I'm not able to write anything, so you might have some questions about the whole process. So Mojit, do you have any question about the calculation of this variance x plus y equal to variance x plus?
No, sir, it is fine. Yeah, fine, sir.
Okay. The next thing that I wrote, and I was supposed to fill in the blanks here, so I was supposed to write in the blank space that if in particular x and y are independent, again, so I will fill the gaps after the lecture, but listen to me. So if x and y are independent, okay, very important clause here. If x and y are independent, then covariance of x and y is 0. So usually covariance of x and y is not 0, but if x and y are independent, then covariance of x and y will be 0. The reason is very simple. The reason is that if x and y are independent, from the previous lecture, you know that expectation of x times y is equal to expectation x times expectation of y from the previous week's lecture actually. So the product of two random variables expectation splits only when x and y are independent from previous lecture. For some there is no problem, but for product expectation of xy is equal to expectation x times expectation y only when x and y are independent. So the statement that I wrote in part C is true only if actually not only if, but in particular if x and y are independent, then covariance of x and y is 0, which implies that if x and y are independent, a very particular case, if x and y are linearly independent, in that case we can drop the covariance term in the sum of the variance formula, and that's what written in that part D. Okay, so in part D it is written that variance of x plus y is equal to variance x plus variance y. Now if you are wondering, previously I wrote variance of x plus y is equal to variance x plus variance y plus 2 times covariance x and y, but that term is not there in part D. It is not there in part D because if I assume that x and y are independent, then I can simply write variance of x plus y is equal to variance x plus variance y. Once again, compare it with expectation. I can write expectation of x plus y is equal to expectation x plus expectation y always, no matter whether x and y are independent or dependent. Expectation of sum of random variable always splits. You can split the expectation without any problem. But for variance of x plus y, you can write as variance x plus variance y if the covariance is 0. Otherwise, there will be this extra covariance term. And this is the important message that I wanted to give in this part 2 of today's lecture. Okay. And then I wanted to do a couple of examples illustrating this dependence and independence fact. So let me go there. The first example is actually again the binomial distribution. So I will fill in the blanks here. So here in the first example, what I said, that suppose x follows binomial NP. Okay, I already gave this example in the part 1 of today's lecture. In the part 1 of today's lecture, I calculated the variance of binomial distribution, which was supposed to be NP times 1 minus p. I'm again doing the same example using a different technique. Okay, and this technique is important, that's why I want to do the same problem using a different technique. Okay, so here I have x, which is binomial NP. Always keep in mind, whenever I say binomial distribution, the model problem is like you are tossing a coin n times, probability of getting head in each trial is p, and this binomial NP counts the total number of heads that you get. Okay. Now, if x is following binomial distribution NP, this x can be written as sum of indicator random variables, and this is the important step here. So x is following binomial NP. I can write this x as summation I is equal to 1 to n xi, and each xi is defined like this. This xi is equal to 1 if we see a head in the ith toss and 0 otherwise. Now if you think about this, this is like the bird problem. So you toss a coin. In the first toss, if you see a head, you count it, you put a tick mark, and you say it is 1. Okay. x1 is equal to 1. Plus, you toss second times, if you see a tail, is 0. Then third toss, if you see a head, you add plus 1. Fourth one, if you see a head, you add plus 1, right? So that's how you count total number of heads in whole n trials. And that's exactly what I'm doing here. The total number of heads in n trials can be written as sum of heads from each trial. Okay, so this xi is 1 if I see a head in the ith toss and 0 otherwise. If I take the sum of all of these xi's from 1 to n, I get total number of heads in the whole n many trials. Okay, the next important clause is that these xi's are all independent. Okay, these xi's are all independent, and therefore I can write variance of x as summation of variance of xi's. Now if you ask, why are all of these xi's independent? Okay, let's think about what these xi's are. So these xi's are counting heads from the ith toss only. Now if you toss a coin, what is happening in second toss is not going to affect what is going to happen in the fifth toss. The tosses of identical coins are independent of each other. So therefore each of these xi's are independent, and therefore, okay, only therefore we can write the variance of x as summation of variance of xi. Otherwise there would be plus this 2 times covariance of xi xs. We do not have those covariances because these tosses are independent. Okay. Another model is that suppose you have an urn which contains 4 white balls and 6 red balls, and you pick balls with replacement, which means you pick a ball, you see the color and put it back to the urn. You pick a ball, see the color and put it back to the urn. So if you do these trials with replacements, the trials are independent. And now if you ask, so if I pick 12 balls, like you pick a ball, put it back, pick a ball, put it back, right? In fact, the first survey problem had this problem that an urn contains 4 red, 6 white balls. You pick balls with replacement, like you do 12 balls, which will follow binomial distribution. Okay, that is a binomial model. If I ask what is the number of red balls you have seen, that will have binomial distribution, and you can solve the variance of that problem using the trick share. However, if you pick balls without replacement, which means you pick a ball, see the color, you do not put it back in the urn, and then you put the next ball and put it aside, and pick the next ball and put it aside. If you do that without replacement, the trials are going to be dependent. If you pick balls from an urn without replacing it back to the urn, the trials are dependent, and in that case we cannot use this sum variance formula because the trials are dependent. Okay. However, in this case, what we have here, the variance of x is written as variance of xi summation. So all we need to figure out is the variance of xi. We use the alternative formula of variance here. So variance of xi is equal to expectation of xi square minus expectation of xi whole square. Expectation of xi square, if you look at the xi random variable, it takes only 2 values, 1 and 0. Therefore expectation of xi square is going to be 1 square times probability xi is equal to 1 plus 0 square probability xi is equal to 0, but we can ignore the 0 square part because if you are multiplying by 0, you don't have any effect. So it is simply 1 square times probability xi is equal to 1. That is expectation of xi square minus expectation of xi whole square. Okay, now what is expectation of xi? Expectation of xi is 1 times probability xi is equal to 1 plus 0 times probability xi is equal to 0. But again, we can ignore the 0 times probability xi is equal to 0 because that is going to be 0 anyway. So it is simply 1 times probability xi is equal to 1 and that whole square. Probability xi is equal to 1. Okay, what is probability xi is equal to 1? Xi takes value 1 only if you get a head in the ith toss. What is the probability of getting a head in the ith toss? It is p. So probability xi is equal to 1 is equal to p, and same is true on the other side, that probability xi is equal to 1 is also p, but you have p square, so you get p square. That is p minus p square, which is p times 1 minus p. So variance of each xi is p times 1 minus p, and therefore variance of binomial distribution x, which is sum of those n many of those, which is n times p times 1 minus p. A very simple calculation. If you compare that with the previous example that I gave, I mean the first calculation of the variance of binomial that I gave in the starting of today's lecture, which was also NP times 1 minus P. This is an alternative technique which gives you the same answer NP times 1 minus P. But I think this technique is very cool, and therefore, you, if possible, you use this technique wherever you can in the variance calculation. Does anyone have any question about this trick here, the variance calculation of binomial again? So obviously we get the same answer as the part 1 lecture, but this is a different trick here.
So what is the
Yes, say that again.
In assignment question, if the balls are picked with replacement and without replacement, both variances are same.
So you mean with replacement and without replacement? Is that what you're asking?
So in both cases, we will use same formula. No? Means variance is same in both cases.
No. See, I was trying to explain if you pick balls without replacement, which means you pick a ball, put it on side, pick a ball, put it on side, those trials are dependent because, see, think about this. So an urn contains 4 red and 6 white ball. So you pick the first ball. What is the probability of getting red? It is 4/6. Okay, put it aside. Then when you are picking the second ball, now there are not 10 balls, there are 9 balls now, and number of red balls might have changed. I don't know. Okay, so that probability of getting red ball in the second trial is not same as the first one, and these are dependent. So if you pick balls with replacement, without replacement, which means you are not replacing back to the urn, you get dependent trials. And if you get dependent trials, you cannot use the sum of the variance formula. You have to have the covariance term. See, I explained that if you have dependent trials, you have covariance. Covariance vanishes when you have independent trials. Right? If you have independent trials, the covariance is 0. And independent trials are with replacement. So you pick a ball. So an urn contains 10 balls. 4 of them are red, 6 of them are white. You pick a ball, you see the color, and put it back to the urn. Now, once you put it back to the urn, when you are going to pick the second time, the urn has the same status as the first time. Right? When you were picking the ball in the first time, it had 10 balls, 4 red, 6 white. But if I put it back in the second time, I also have 10 balls, 4 red, 6 white. And again, if I put it back, so every time when I'm doing the experiment, I have 10 balls, 4 red, 6 white. So if I do with replacement, if I'm placing it back, the urn is getting back to its original status. Therefore, what I see in the first trial is not going to affect what I'm going to see in the second trial. So with replacement, trials are independent. So with replacement, trials are independent. Therefore, you can split the variance. Without replacement, trials are dependent. Therefore, we cannot write the variance as the sum of variances. In fact, there will be extra covariance term. Am I clear?
In fact, extra covariance term is there or not for binomial distribution, whether it is dependent or independent. Variance formula is n into p into 1 minus p. No.
Yes. So for binomial distributions are trials with replacement. Okay. So whenever you are picking balls with replacement, like you are putting it back each time, that model is binomial distribution. If you do without replacement, that model anyway doesn't follow the binomial distribution. So that answer is going to be different anyway. That model will not follow binomial distribution at the first place. Okay. Yeah. So if I tell you the next example, it will be actually more clear. The next example is the BART problem, and I talk about this example in the expectation classes when I was doing expectation. So recall this problem. This problem is that, so there are n BARTs sitting in a row. Each BART looks to the left or to its right with probability 1/2. And we count the number of BARTs who are seen by their immediate neighbors. Okay. For example, if I look at the first BART is not seen by any of its. Actually, it has only one neighbor. Therefore, I put I1 is equal to 0. If I look at the second bird is seen by its neighbor, the first bird. Therefore, I put I2 is equal to 1. If I look at third bird, so third bird has two neighbors, the second and the fourth. Third bird is seen by one of its neighbor, which is the second bird. Therefore, I3 is equal to 1. Although the fourth bird is not looking at the third bird, but it doesn't matter. If at least one of the neighbors is looking at him, we say this bird is seen by its neighbor. For I4th has fourth bird has two neighbors, third and fifth. You see that this third bird is looking away. It is not looking to the fourth bird. And fifth bird, we don't know, the picture is not there. If the fifth bird is looking to this fourth bird, then I4 is 1. If the fifth bird is looking away, then I4 is going to be 0, and so on. And that's how we define this indicator variables II. So I already did this when I was doing the expectation in the previous week's lecture, but again. So II is equal to 1 if the ith bird is seen by at least one of its neighbor, and it is 0 otherwise. Okay, and this yi, which is the sum of total number of birds which are seen by at least one of its neighbors. Now, can we write, if I want to find a variance, can we write variance of y as summation of variance of ii? Okay, in the previous week's lecture, we have seen that we can write expectation of y as summation of expectation ii. No problem, expectation can always be split. But can we write variance of y as summation of variance of I? The answer is no. Why the answer is no? Because these ii's, the indicator variables, are dependent. Okay, these variables are dependent. Why are they dependent? Okay, so let's think about this. Let's look at I2 and I4, the second bird and the fourth bird. Okay, second bird and the fourth bird. So if you look at the second bird, I2 could be 1 if the third bird is looking at this second bird, which would mean that the third bird is not looking at the fourth bird, which may indicate that I4 is equal to 0. So in a way, the status of the second bird and the status of the fourth bird depends on whether the third bird is looking at left or right. Of course, it also depends on the first and the fifth bird, but there is a dependence via the third bird, right? So you see that the status of second and fourth are dependent, and so on. So status of I3 and I4 are also dependent. If you take ii's far apart, so maybe like I2 and I100 will be independent because I2 depends on its two consecutive neighbors. I100 depends on 99th bird and 100 and first bird. So in that case, they will be independent. But if ii's are close enough, then ii's will be dependent. And since they are dependent, we cannot write the variance of y as summation of variance ii because they are dependent. In fact, there will be covariance term. Which is variance of y will be variance summation of variance ii plus covariance between all possible ii and ij. Okay, this sum is a huge sum. The covariance of ii, ij is huge sum. You have to consider covariance between I1, I2, I1, I3, I1, I4, I1, I5, and so on. And again, then I2, I3, I2, I4, I4, and so on. So all possible pairs, covariance, all the covariance terms will be there in the whole sum because they are not independent. Okay, so few of them are maybe independent. So in that case, those covariance terms will be 0. For example, I2 and I10 may be independent, like the status of second bird depends on only first and third bird, and status of 10th bird depends on only 9th and 11th bird. So there is no intersection, and those will be independent. So covariance between I2 and I10 will be 0 maybe, but there will be some non-zero covariances, that like covariance between I2 and I3 will be something non-zero. So we need to calculate that to figure out the actual variance of this y. Okay. So let me stop here. I will fill in the blanks. So whatever I said in voice, I will write those in the blanks, and you have the survey form, so you can take the survey now. Okay, actually, before stopping, let me write down. Let me tell one small thing. This is related to covariance, which is called correlation coefficient, which is kind of covariance, but so correlation coefficient between x and y is covariance divided by square root of their variances. Correlation coefficient also denotes the linear dependence between x and y. And there is a homework problem for you, which says that covariance of xy whole square is less than or equal to variance x plus variance y, and that would imply that covariance of xy is bigger than or equal to negative of square root of variance x square root of variance y, and less than or equal to square root of variance x square root of variance y. Essentially, what would it mean is that correlation coefficient is always between -1 and 1. So the main difference between correlation coefficient and covariance is that covariance could be anything. It could be -100, it could be positive 1 million, whatever. And to overcome that, we divide it by square root of the variances so that it always stays between -1 and 1. So correlation coefficient also measures the dependence like covariance. Covariance measures the dependence, linear dependence between x and y. Same correlation coefficient, it measures the dependence, linear dependence between x and y. But we are dividing it by square root of the variances so that the answer is always between -1 and 1, so that we can compare the answers, like the magnitude of dependence. If the correlation coefficient is close to 1, we say that they are highly dependent. If it is close to 0, we say that they are not so dependent, and so on. If it is close to -1, we say that they are inversely dependent, like one is increasing, other is decreasing. If it is close to 0, they are not so dependent. So there is not that much difference between correlation coefficient and the covariance. Only difference is that we are dividing it by the square root of the variance. Okay, so let me stop here. I will fill in the blanks. Whatever I said, I will type those up after this lecture, and you can access that through the link, lecture note link that I have already sent you. So you will see whatever I said, I will fill in the blanks and I will type it in. So if you have any question, you can ask me, or there is a simple problem in the survey part 2, and you can take the survey. Okay, if you do not have any question, I will close the session after 2 minutes. And the survey form will close, I think, around 11 or 11:04, something like that. But there is only one single problem, so you should be able to write this before 11. So I will wait for 2 minutes. If you do not have any question, I will close the session after 2 minutes.